this example problem, we are told that we push with a force of 35 newtons a block across the floor for a distance of 3 meters. Part A asks us, what is the increase in energy of the block floor system? Now, the way I am going to think about part A of this example problem, let's suppose here is the floor and here is the block. I am pushing on the block, and in pushing the block, I am doing work on the block. So we said you could imagine doing work on something could be interpreted as giving energy to that object. So the act of me pushing on the block will increase the energy of the block floor system. The block and floor are allowed to trade energy between each other. So the energy I give to the block could then, in principle, be transferred to the floor. And depending on how elaborate you want to make a problem, you could imagine a scenario where some of the energy might go back to the block. But the important thing for part A of this problem is I am putting energy into the block floor system. So I am inserting energy here. So how much energy do I give to the block floor system? That is basically asking, what is the work that I do? How much energy do I give? So the work done by my push is equal to the force of my push times the displacement of the block times the cosine of the angle between the direction of my push and the displacement vector d. So in this particular problem, the work done by my push will be equal to the strength of my force is 35, the displacement of the block is 3 meters, and the angle between my push and the displacement vector d is 0 degrees. These two vectors are parallel with each other. So I would write cosine of 0. Now when I put these numbers in a calculator, the work of my push is 105 joules. So I am giving 105 joules of energy into the block floor system. In part B of this problem, we are going to investigate what happens to the 105 joules that I give away to the block floor system. Of this 105 joules, some of that energy is going to go into the block's motion. So I could say some of that energy will go to the kinetic energy of the block. But all 105 joules are not going to go to the block's kinetic energy. Some amount of this energy is going to cause an increase in thermal energy of the block or the floor. And so some of this energy is essentially going to be wasted. So within this thermal energy, some of it will go to the block and some of it will go to the floor. Now, if I add up the amount of energy that increases the floor's thermal energy and the amount of energy that goes to increasing the block's thermal energy and the amount of energy that the block gains in the form of kinetic energy, these three energies should add up to 105 joules. This is much closer to a real-world scenario than some other problems that we have considered. If we wanted this example to be a perfect real-world scenario, then we would also have to account for air resistance. Moving through a fluid would cause turbulence in the air, and that would be like friction, tending to sap away some energy from the block. Moving through across the floor would also create sound. That would be another source of energy being dissipated away that cannot be recovered. But for the purpose of this example problem, we are assuming that of this 105 joules that I give to the block, some of that energy goes to the block's kinetic energy, some of that energy is dissipated away by friction in the form of thermal energy. And of that energy that friction dissipates away, some of it will go to the block, the rest of it will go into the floor, causing the temperature of the block and the floor to rise. So how much thermal energy is dissipated away by friction? To answer that question, we need to know the work done by friction. So I would write the work done by friction as the force of friction times the displacement times the cosine of the angle between the displacement vector and the force of friction vector. We know the displacement is 3 meters. We know that the displacement vector points to the right and the friction vector points to the left. These vectors are opposite, so my angle is going to be 180 degrees. All we need to do is we need to find what the force of friction is going to be. To find the force of friction, this is essentially a Newton's second law, chapter 4 forces problem. So I recognize that the block is not accelerating in the y direction at all. It is just sliding across the floor horizontally. So I recognize that AY is equal to 0. And so I could say F net Y is equal to 0 because AY is 0. Now, in the upward direction, I have the normal force. I have the gravitational force pointing downward. And these two forces have no component in the y direction or a component of 0. So plus 0 is equal to 0. And I find that the normal force is going to be equal to the block's mass, 4 times 9.8. And so the normal force on the block in this particular example is 39.2 newtons. Hypothetically, if we were pulling the block along the ground, but with a string that is angled, we would also need to account for the vertical component of the tension force in finding F normal. But for this particular example, that's one extra complication that we don't need to worry about. We can now find the strength of the force of friction on the block. The force of friction is given as mu times F normal. The coefficient of friction, mu, we were given in this problem, that is 0.6. And the normal force on the block we just found to be 39.2. So if I put these numbers in a calculator, I find the force of friction is 23.5 newtons. Again, we are only caring about the strength of the friction force. We don't really worry about direction. We will account for direction when we insert this angle theta for finding the work done by friction. So I could write the work done by friction to be the strength of the friction force, 23.5, times the displacement of the block, 3, times the cosine of the angle between the direction of the friction force and the direction of the displacement. So that would be cosine of 180 degrees. And if I put these numbers in a calculator, I find the work done by friction is negative 70.5 joules. So in this problem, we found that our push does 105 joules of work. That is essentially saying that on account of us pushing on the block, we are giving 105 joules of energy to the block floor system. So we inserted 105 joules of energy into the block floor system. We could now ask what happens to that 105 joules that we give to the block floor system. Well, of that 105 joules that we give, some of that energy is going to go into the block's motion. So some of that energy goes to the kinetic energy of the block. But some of that energy is going to be dissipated away by friction. The amount of energy that friction dissipates away is 70.5 joules. So I could say that 70.5 joules will be converted into thermal energy. Friction is a force that dissipates energy away, and the act of the block and the floor rubbing on each other causes an increase in the thermal energy of these two objects. The thermal energy increase of the block does not need to be the same as the thermal energy increase of the floor because they are made of different substances. One object might be a better conductor of heat than the other. But still, in total, friction is the force that dissipates away or steals away 70.5 joules of energy, and friction essentially converts that useful energy into an unrecoverable form, thermal energy in this case. So what happens to this 70.5 joules of thermal energy? Well, of the 70.5 joules of thermal energy, we were told that 40 joules go to the block. And if 40 joules of energy go to the block, then I could infer that the rest of this 70.5 joules of energy have to go to the floor. So I could infer that then 30.5 joules of energy have to go to the floor, because 30.5 plus 40 gives me 70.5. For part C of this problem, we are asked, what is the increase in the block's kinetic energy? One way we could see this question right away is we could say, well, of the 105 joules, 70.5 of those joules went to thermal energy, so the rest of that energy had to go to the kinetic energy of the block. So I could say that 105 minus 70.5 equals 34.5 joules, and this is the increase in the block's kinetic energy. And this is the correct answer. There is another more physics formal way we could demonstrate this. Let's remember the work kinetic energy theorem. So the work kinetic energy theorem, W net equals delta KE. In this problem, I have 4 forces acting on the block, and each force will do some amount of work. Some of those forces might do 0 work, but I'm going to include them in W net just to be very thorough. So I could say the work of my push plus the work done by friction plus the work done by gravity plus the work done by the normal force must equal the change in the block's kinetic energy. Now, the work done by gravity and the work done by the normal force are both going to be 0. I could see that just by looking at this picture. We said that work could be written as FD cos theta. And whenever the direction of the displacement vector is perpendicular to the direction of the force vector, we'll have cosine of 90, and cosine of 90 is equal to 0. So the work done by gravity and the work done by the normal force are both going to be 0. The work done by my push I found to be 105 joules. The work done by friction is negative 70.5 joules. Plus 0, that gives me delta KE. And so again, I find the increase in the block's kinetic energy is going to be 34.5 joules.